In this video, I want to talk about the ambiguous case for the law of sines. If you recall, the law of sines is a very useful tool for us. It allows us to find missing pieces of many triangles, and they do not have to be right triangles. Generally, if you recall how it works, we'll put together any two of the ratios of the law of sine. Assuming we know 3 of the 4 of these pieces, we can then find the 4th missing piece somehow. However, sometimes no matter what variation of these you put together, you might always have 2 missing pieces, in which case you can't solve the equation. But if that's the case, then we just rely on law of cosines. In a case where law of sines isn't working for us because there's too many unknowns, generally the law of cosines will work for us, and vice versa. If you're stuck using law of cosines, it's not working, try using law of sines. You probably have enough information to use that. Okay, so one of the big things we want to be able to do with law of sines or cosines is, given some information about a triangle, be able to find all the other missing parts, right? Be able to solve the triangle. For most problems, it's really straightforward. Take the diagram they give you or the information they give you, use the appropriate law, sines or cosines, maybe both, and go find the missing pieces. However, there's a case where you do need to stay on your toes, and it does require some more investigation. And that's the case when you are given information about a triangle, including its side, and an angle. And more specifically, that angle and one of those sides are opposite one another. So if you have the case where you know 2 sides and an angle, and that angle is opposite one of those sides, you're looking at the ambiguous case. Okay. So that's all I've drawn down here is a bunch of pictures where I've got 2 known sides and an angle, and that angle is opposite one of those sides. Books always present it this way, side, angle. To be honest, I remember it this way, angle, side, because it helps me remember that this is the case that is a pain in the angle, side. Okay. So let's see why this is known as the ambiguous case. When you are given angle, side, and again, one of those sides is opposite that angle, let's see why we have to do a little more investigation. Take a look at this first diagram here, number 1. There's some baseline that's drawn, right? And from there, I'm going to draw a segment of length 10 at an angle 30 degrees off baseline. So this is all information that's given. Let's say I drew I've got a 10-foot pole going up this way, and then maybe you give me 2 feet of rope. Well, the question becomes, is that 2 feet of rope even long enough to make it all the way down to the ground, to the baseline there? In other words, do we even have a triangle? That's why all these diagrams have been drawn with dotted lines, because we really don't know if that extra third side, or sorry, if that second side there is long enough to even make it down and close off the triangle. So we first have to begin investigating that. Can it make it? Well, to do that, we have to figure out what's the quickest way to close off the triangle. And that would be the height of the triangle, right? From this point up here straight down would be the shortest distance, or the very least amount of rope I would need to close off and actually make a triangle. So we need to figure out what that is, what that little height is. But since I've dropped a height, in here I am looking at a right triangle, so I could use things like SOHCAHTOA. Can't use SOHCAHTOA here because it's not a right triangle. There is no hypotenuse. But in this little yellow triangle, I can. We could use that to find the height. So in that triangle, I could say that sine of 30 degrees would equal opposite over hypotenuse. And so if I move the 10 over, let's see, sine of 30 is a half. So this means that the height of that triangle is 5. You need 5 feet of rope to close off that triangle. So that means up here in this problem number 1, if I need 5 feet of rope to get down to close off the triangle, 2 feet of rope isn't going to cut it. There's no triangle here. There's nothing to solve because there's not even a triangle. We don't have enough length on that additional side there. So move on, nothing to find there. Let's look at question number 2 here. I'm using all the same numbers, the 30-degree angle and the side length 10. I'm just changing this number here on the outside. So we could talk about what that length of rope does to us here. In this second case, again, angle, side, side. One of those sides is opposite the angle. So it's the ambiguous case. It's the pane in the angle side side. We have to investigate and see, is 5 feet of rope enough to close off the triangle? From our work earlier, we know that it is. It's exactly enough. So really that picture should be updated. Really what you're looking at is a 30-degree angle here. This was 10. And because I have exactly 5 feet of rope on this side, right? It must be that that's flat out the height of the triangle. So really, in this case, you've got a right triangle, in which case to find any missing pieces like this side length here or this angle here, you could just use SOHCAHTOA, right? Because you're in a right triangle. There is a hypotenuse. However, you could still use law of sines, law of cosines. Those always work. But if you're in a right triangle, SOHCAHTOA is generally faster. Okay, so here we have one right triangle. We have one right triangle, and then with a little bit of trig, we can find the missing pieces. Okay, let's look at question number 3 or scenario number 3. Again, angle, side, side. It's still the pane in the angle, side, side case because I've got an angle opposite that side. We're still working with a 30-degree angle and a 10-foot pole here. So we don't have to rework the math. We already determined that the minimum distance needed here is 5 feet to close off the gap. And actually, in this case, I don't even really need to think about it. To get to this point from this baseline, okay, however, whatever the base is that this triangle is sitting on, to go from this corner to this point required only 10 feet of rope, let's say, or it's a 10-foot pole. So now you're going to hand me 15 feet of rope. That thing can definitely make it. If 10 feet of rope can get to the baseline, then 15 feet of rope can definitely get to the baseline. And more importantly, that's the only place it can go. It's got to go there. After we look at question 4, we might want to relook at number 3 and wonder, can it go anywhere else? But I couldn't connect to the baseline here because that green line would have to be shorter than the blue line, right? The blue line is 10. The green line I've drawn here to the left of the height 5 would have to be smaller than 10. So it can't fit 15 in there. So the only place we can go is here or something like that. We have one triangle, but it's not a right triangle. So to solve this triangle, we would have to use law of sines. Maybe we'll need law of cosines. Sometimes you need both, but we can use law of sines and we could dig out the missing pieces. We cannot use SOHCAHTOA because we do not have a right triangle. Okay, let's look at number 4. And this truly is the one that's probably the most pain. Last scenario, same angle, same side, still angle side side case. Because this angle is 30 and this side is 10, again, using our previous work, we know the minimum distance needed to close off the triangle is 5. So 7 can do it. 7 definitely has enough length to close off the triangle. Here's the issue. We know that any segment that goes this way, though, is going to be shorter than 10, but longer than 5, right? If it's got a 5 is the straight down distance, 10 is the distance way out here to the left. So anything going in between them would be somewhere in between 5 and 10, a length of 5 and 10, which 7 fits the bill. So in other words, 7 feet of rope could also be extended this way. And in this case, we're actually looking at 2 triangles. We have this triangle this big outer triangle here. But we also have this little weird shaped triangle here. Both of those would satisfy angle side side of 30 degrees, 10, and 7, right? The 7 could go out here, or the 7 could fit here. And so you have two different triangles that are described this way. See if I could fix the picture. Here's the little weird looking triangle. This was 30 degrees, this was 10, and this was 7. Or we've got the big outer triangle where this is 30 degrees, 10, and this is 7. And so you would need to solve both of these triangles. This now becomes two problems. You'll see that there is some overlap though. When you use some inverse trig to dig up a missing angle, remember that when you use inverse trig, like for example, sine inverse, your calculator is only going to tell you an answer between those two quadrants because of the domain restrictions. There's always, or I guess I'd say very often, another angle solution that works that the calculator just can't address because of the domain restrictions. So this is where the overlap is going to come in. When you're looking for this angle, that's going to clue you in on what other angle would be useful in the other triangle. Okay, so I hope this helps clear up a little bit of the ambiguity of this case, but for other cases, just dig right in. But when you encounter an angle side side scenario, know that you've got to dig a little deeper and determine, do you even have a triangle? Do you have one triangle? Or maybe you have two triangles, and then you can go solve whatever case you're presented with. Okay, keep up the good work.